Добрый вечер.
Добрый вечер.
Добрый вечер.
So people are here, or it's just black squares?
Some people must be here.
That depends on the meaning of here.
Yes. Mentally here, not physically.
At least.
Так чего? Где вообще все? Вот это самое.
Все тут.
Так ну включи камеру, как-то так это самое, чтобы было видно, что граждане здесь.
Ну, у меня камеры нет на большом компьютере.
У меня камера есть, но я предпочитаю слушать лежа, и вид у меня не очень презентабельный.
Ну, хорошо.
Я включу, но я тут...
Нет, но не то, что это не просто как-то так, я думаю, что докладчикам...
Но, тем не менее, приятно всех увидеть.
Да, докладчикам, наверное, самое приятнее, если он видит, что все в задумчивости, и, значит, не понимает, что он говорит.
Ну, вообще, можно, наверное, начать.
Да, давайте.
Чего мы ждем?
Okay, so let's start now.
Okay, fine. So even if I cannot see you, I hope I can hear you. So if anything is not clear or you want to add any comment, just do not hesitate to interrupt me at any moment. Okay. I will first remind very quickly what we have done last time, 2 weeks ago. So we are talking about the definition of the information distance between two constructive objects, or more specifically between two binary strings, introduced by Bennett, Levy, Tani, Zurich, and Gatch. There are two definitions that are not exactly equivalent, but that give the same value up to an additive logarithmic term. The first definition is just the maximum of two conditional complexities. That is a maximum of the lengths of optimal programs that convert y to x and x to y. And another definition is the minimal length of a program that can do alone both these tasks. It can convert x to y and y to x. Okay, I will skip these pictures from Vitani's paper, and we discuss the property of clusters with respect to this distance. So once again, what is the cluster? Cluster with two parameters, m and l. It's a set such that the distance between any two objects in these two sets is bounded by the first parameter, and the size is at least exponent of the second parameter. And we're typically interested in the situation when these two parameters are quite close to each other, when the difference between the diameter of the cluster and the log size of the cluster is a constant, or maybe a logarithmic term, but it must be somehow small. And first of all, we observed that there is an obvious trivial construction of a cluster with parameters m and l that are close to each other. We can take the kernel z, and then we can consider the set of all say concatenations y z such that complexity of y is bounded by m.
Or just simpler, just the strings of length m, if we are, anyway we make concatenation, so it's not invariant thing.
Or if you want a more invariant definition, you can define it like that. It will be okay, s hat. You can take all x's such that this kernel z is a very simple conditional on this x, and complexity of x given z is at most m. So in the first example, the construction is kind of it's connected with the structure of strings, and in the second example we do almost the same thing, but we just refer to the conditional complexities. Okay, so we will say that such a thing, it's a canonical cluster. So what can we do besides the canonical clusters? Of course, we can take a subset of canonical clusters. We can take a half of all strings in the canonical cluster, or some large fraction. It will be still a cluster with the same diameter m, and the size could become slightly smaller. And we asked ourselves whether there exists something significantly different, whether we can find a dense cluster where the parameters m and l are quite close to each other, and such that this is not a canonical cluster, this is not a large subset, a canonical cluster, such that the structure is completely different. And we proved the statement which, roughly speaking, says that it is impossible that all dense clusters where parameters m and l are close, they all looks like that and not like that. This was the theorem that we have proven last time. And today my plan is to discuss one or two applications of this theorem. So if you have questions about the definition of a cluster or about the statement of this theorem, then it is the right moment to complain and to say something. No?
No,
Everyone is happy?
I can just say that this is kind of very interesting theorem, since the construction of this Z is quite strange and not very traditional. So it's obtained from an enumeration of a very large objects.
It sounds like some critics. You do not approve this, as you say, strange construction.
No.
Do you mean there must be some or more
It's
natural
interesting.
proof?
No, I don't know. But for example, if we want to to get some kind of a bounded complexity version, imagine that we have a big cluster of big set of strings with small conditional complexity with some, I don't know, polynomial space bound or something like this. And then can we hope that there exists a kernel?
I don't know.
No, definitely it exists with unlimited complexity, but is it possible to find a kernel like this?
No, I don't know.
So usually results about complexity, at least with space bound, they often remain more or less the same. And for this, and usually the proof kind of can be somehow adapted, but here it doesn't look like the proof can be adapted.
Yeah, at least it's not obvious at all that we can adapt the proof. I can imagine that a more constructive proof could exist, which could be adapted for a resource-bounded version of Kolmogorov complexity. But then it must be pretty different. I guess then we cannot just in the proof of the theorem we have chosen a list of some very special referential clusters which have a large intersection with any other cluster in the world. So perhaps instead of we constructed them somehow by some kind of iterative process. Maybe instead of this iterative process, we could use some sort of I don't know, heating set, just drop at random some sequence of kernels, and hope that if these kernels are chosen by a pretty random or pseudo-random function, then they also can be used as this list of referential clusters that intersect with everything or with almost everything. But this is a pure speculation. I have no proof of a resource-bounded version of this theorem.
Yeah.
By the way, there is a small echo. It is not terribly bad, so I can continue speaking. But if somebody complains, we can try to find the reason and to fix it.
But now there is the reason or not? The echo, not the reason.
Yeah. When you are speaking, I see the echo.
It's
I
strange.
don't.
No, maybe someone uses not the
I think there are only two participants with muted microphones, you and me.
but that's very strange because okay,
Okay. Now there are 3.
I can mute if it helps, but
1, 2, 3. Okay. Let's proceed. So we have this theorem. We have proven this theorem. It was a proof. Okay. A proof. Yeah. So last time we stopped somewhere here. And now I'm going to apply this theorem to get some finite corollary. Before I will formulate a finite corollary, I want to say a few words about about a kind of favorite question of our seminar. It's about common information. Common information. Which should not be confused with the usual mutual information, or about this property of extracting or materializing of the mutual information. So what is the mutual information, or what is the information in X about Y by definition? By definition, it is the difference between complexity of Y and complexity of Y given X. And a symmetric guy, the information in Y on X, this is the difference between the plane complexity of X and complexity of X given Y. And formally speaking, these two terms are different. They're not exactly equal to each other. But both these terms, both these expressions, they are close to the symmetric version of the mutual information. It is the sum of complexities of X and Y with plus, minus complexity of the pair. And the precision of these equations is logarithmic. It's bounded by big O over log n, where n, let us say that n is the sum of lengths of X and Y. Or we can take complexity of the pair X, Y. And in some cases, in some naive examples of X and Y, these mutual information as a clear intuitive meaning. So let us say that x and y have equal prefixes of length n/2, n/2, and the suffixes also of length over 2 are completely different and has nothing to do with each other. Then the fact that the first halves of x and y are identical, it explains why the mutual information between x and y is pretty large, something like n/2. So in this case, the mutual information between x and y can be materialized just as the common prefix of both these strings. However, this is not always the case. There exist pairs x and y with a huge mutual information, but such that this mutual information is somehow distributed between x and y in a subtle way, and it is impossible to represent it as one object. And there are two standard examples of such x and y. We can take x and y of length n bits, such that the Hamming distance, it's not the information distance, just the standard Hamming distance between x and y is something around 11% of the length. Then it turns out first, it is not surprising that x and y share some mutual information. So if we know x, then it is easy to specify y somewhere around x. This is simpler, this is easier than to produce such a y from the scratch. And I have chosen this. Okay, it's clear that the smaller the distance, the bigger is the mutual information. And if we choose the constant here, this 0.11, if we choose this constant in a proper way, then the mutual information between x and y is just a half of their length. And in this case, it's not so simple to prove, but it's quite easy to believe that in this example it's impossible to materialize this mutual information. We cannot find an object of length n/2 bits such that these objects is somehow a part of x and at the same time a part of y. This is the first example. And the second standard example is a more algebraic one. Let us take, if we want to have x and y of the same size, of the same complexity, it should be a finite plane over the field. It should be a finite field with 2 to the n over 2 elements. And then we can say that x is a polynomial of degree 1 over this field, so a line in this plane, and y is a point in this plane incident to this line. Then we have the same complexities of x and y as in example 1. To specify x, we need two parameters, two elements of the field, so we need n plus 2 and one more n plus 2 bits. And the same is true for y. And the mutual information is also about n over 2, since when we know x, we need only one parameter, one element of the field to specify y. So in example 1 and in example 2, we have pairs x and y, and in this example 0. In all these three examples, we have x and y with the same complexity profile. Complexities of x are n, complexity of y is n, the mutual information between x and y is n over 2, but in example 0, these mutual information of size n over 2 is obviously extractable. In example 1 and example 2, it is not extractable. And once again, okay, I just claimed that it is not extractable. It's quite easy to believe, but a formal proof requires some argument. But it is well known. So, for example, one, it is known since 1970s. It was proven by Gatch and Körner, and later Alsweder with Gatch and Körner. They showed that for this pair x and y, we cannot materialize their mutual information, or as Gatch and Körner used to say, common information is far less than the mutual information. And for example, too, it was Andrei Muchnik who showed in 80s that for this algebraic construction of x and y, the mutual information is not materializable. So the common information is also far less than the mutual information. So it was a story of pairs, and here there are no clusters. No clusters, just a pair of negative results. And these negative results that show that, at least in a typical situation, it is not such a nice situation as this trivial example 0. The mutual information has no direct physical meaning. It is just an algebraic expression of the difference between two complexities, or this algebraic expression, which is a combination of three complexities. And now I'm going to show that for a triple of strings, in some cases, if we know something about complexities of x, y, and z, we can guarantee that the mutual information between x, y, and z cannot be materialized, and their mutual information is the same as their common information. Okay, just before we look at the formulas, I propose to look at the picture. So, in this picture, I am going to represent the complexity profile of x, y, and z. So, I'm going to talk about x, y, and z such that complexity of x given y and z is, I don't know, n1. Complexity of y given x and z is n2. Complexity of z given x and y is n3. The complexity of the entire triple is n1 plus n2 plus n3 plus n0, and that's all. The gray parts of this diagram, they show that the conditional mutual information, for example, okay, if you remember this notation, the conditional mutual information between x and y given z is negligibly small. Or in
Which
other
is
terms,
epsilon in the formula.
yeah, what here it is written as epsilon. Yeah, it is epsilon, which is small. and the same for x and z given y, and the same for the mutual information of y and z given x. Or the same property can be restated as follows: the mutual information between x and y, which corresponds to this part on my diagram, it is more or less n0. So n0, this part n0, it represents the mutual information between x and y. It is the same the mutual information between x and z, and the same as the mutual information between y and z. And the same, if you like this non-conventional notation for the mutual information of a triple, then we can say that the mutual information of the triple is also n0.
So just if you want to say in one sentence, I guess the theorem says that there is a case when we take some string of length n0, and that add independently 3 strings of length complexity n1, n2, n3, and then consider pairs n0, n1, n0, n2, n0, n3. And so for such a thing, the diagram is like it's written.
Yeah.
And then your theorem says the reverse. If the diagram is like it's written, then actually our x, y, and z can be represented in this form. There is like some common string of complexity n0 and 3 independent, relatively with known first string. They are independent and have complexity n1, n2, n3. So there is a kind of total complexity characterizations of triples like this.
Yeah. Or just I will repeat the same thing in different terms. If the three conditional mutual informations here are bounded by small epsilon, then there exists a common information, I don't know, W, whose size is n0 from the central part of the diagram, such that this W is a simple conditional on x, conditional on y, and conditional on z. All these 3 terms are small. How small? Small like that.
It's natural that we don't have logarithm epsilon, because epsilon just is the precision in not length,
epsilon is just the
error.
precision of epsilon shows how small are the 3 conditional mutual informations, the gray parts, light gray parts in my diagram.
And c is just what usually is written like logarithm of O of log n for length. So it's also not necessary to make the mutual information well defined.
Yeah, as usual, we must add this log n term everywhere. Okay, now I finish my explanation, and if you like, you can read just the letters and the formulas, just the formal statement of the theorem. And if anyone has a question, then I'm happy to answer it. Any question? No, it seems that everyone is fine with this statement. So are we okay with the statement of the theorem, or it's not clear enough?
No, I don't know. We should ask somebody specific. But I don't know who
Yeah, I think it's clear.
Okay. Yeah, okay, just before we proceed with the
We
proof.
don't have Sasha Kazachinsky, or he's hidden under some name or not.
Sasha Kazachinsky.
Kazachinsky is missing.
Missing.
No
That's
Kazachinsky.
bad. Okay.
Okay, just the last, before I start the proof, the last phrase, which is an advertising of the theorem. If we go back to the examples of pairs with extractable and non-extractable mutual information, you see that in example 0, 1, and 2, we have pairs with exactly the same complexity profiles. But in one case, the mutual information is extractable, and to other cases, it is not. So, given the complexity profile, we cannot predict the structural property of this pair. We don't know whether the mutual information is extractable or not. And for triple, we have this funny property that it is enough to know that the three values of the conditional mutual information are negligibly small, and then we can predict the structural property of the triple. We know that the mutual information is extractable. Okay, maybe before I switch to the next page, somebody who hasn't seen this the proof of this theorem can predict how do we use the clusters here. Right now there is no clusters. We have only 3 strings. It's not enough to find the kernel in a dense cluster. Are there any predictions where the clusters come from?
No, definitely you already told me this, but I forgot everything. But maybe you just
very well.
consider,
So you
consider.
you can pretend that you invented yourself right now from nothing.
No, but no. The one possibility is to fix 2 strings and consider 3 strings which have this profile. But of course they are not a cluster. So
why of course it will be not a cluster?
no, because
Okay, just sorry, just a minute. I repeat the Sasha suggestions. Sasha suggests to fix x and to fix y, and to variate z. To variate z, take not one z that we were given at the very beginning, but take many other strings z that would form a similar diagram of complexities together with the fixed x and y. So we will have not one single z, but lots of different z. But then Sasha claims that it will not work because
no. It's not. Maybe no. It's not clear how to see that it's a cluster. But who knows?
Okay, who knows? Let us try Sasha's plan. Just I will repeat what he suggested in more formal terms. I already used this expression complexity profile. What is a complexity profile? Say for a triple. What's complexity profile for x, y, and z? It is a tuple of 7 integer numbers. All possible complexities involving x, y, and z. Complexity of each string, complexity of each pair, and complexity of the triple. And as Sasha suggested, I will fix x and y and take many different clones of siblings of z. I will take all z such that complexity profile of x, y, and the sibling of z, it looks almost the same as complexity profile of the real triple, of the real original triple x, y, and z without prime. Here is a small delta here. Delta means that in each of these 7 coordinates, the difference between complexity of z and z prime, complexity of xz and xz prime, etc., 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 the difference in each coordinate should be bounded by delta. And delta will be logarithmic. So if n is a complexity of x, y, and z, then delta will be of order log n. Oh, actually, I can define this set of siblings of or clones for any delta. But I prefer, and here I have actually I would like to make it as small as possible. So z must be as similar to the real z, to the real z, z prime should be as similar to the real z as possible. But it turns out that I cannot I cannot say that the delta is just exactly 0. But if I take it logarithmic, then the set of clones will be pretty large. What is written here? It is the size of the set of clones. First of all, it certainly cannot be bigger than complexity of z given x, y. Okay, maybe plus something logarithmic. Maybe as an exercise, somebody can explain why the set of clones cannot be much bigger than 2 to the conditional complexity of z. Okay,
But just the profile says this somehow.
Okay. If you want to be very, very formal, then I would say you that in the profile there is no conditional complexity. Technically speaking, we do not claim that conditional complexity of z prime given xy is the same as complexity of z given xy. But of course we know that complexity of z prime given xy, it is the difference between complexity of x, y, z prime and complexity of x, y with a logarithmic precision. And by the definition of a clone, this is complexity of x, y, z without prime minus complexity of x, y plus log n and plus or minus delta. So you're right, the definition of a profile says slightly indirectly that complexity of z prime given xy is mostly the same as complexity of z, of the original z given xy. And of course, the number of z prime, with such a property is not bigger than 2 to the complexity of just 2 to the all this stuff. So it cannot be bigger. and it is quite direct and quite trivial. And it turns out that if delta is not ridiculously small, if it is just some log n with some with reasonably chosen constant here in this big O term, then it cannot be much, it cannot be smaller.
No, and if delta is ridiculously small, it's even smaller.
No. The claim is that it is not just my claim. It is not that it is bounded, upper bounded by this term. The claim.
Yeah. So you speak about lower bound, yeah.
Yeah. So we can write equation here. Actually, it's not a deep fact. It's just quite a standard counting argument that we have seen many times in many different situations. I don't know. Do you want to believe me, or we will discuss the proof of this fact in more
No,
detail?
I think we may let someone, for example, Kolya, guess how the argument works. So why imagine that there are only few of them.
Then the complexity of Z is small,
Then
smaller
knowing
than
X and Y, we can enumerate all these things.
Yeah, indeed. If first of all, when X and Y are known, then we can run a process which enumerates the set of clones. Okay, if I'm cheating a little bit, we can enumerate some superset of the set of clones. We can enumerate all Z prime such that in the complexity profile is maybe not exactly the same as we want, but not bigger than what we want. If we want this property to be enumerable, then we should write only an upper bound for each coordinate. So if this set is too small, then every element in this set has a small complexity given X and Y, and then this equation cannot be true. This is the idea, but technical implementation of this idea requires to update the definition of a complexity profile and to say that let us require that each coordinate is not exactly is not equal to what we want with the precision delta, but it is upper bounded by this term, and then we have to write in this profile not only simple complexities but also conditional complexities, and there will be some boring stuff like that. So nothing
but
really.
still there is a question. If we consider strings which are have smaller the bound for complexity profile, there are many of them, but you claim that there are many for given profile.
Okay,
There is it's also standard thing, but what do you say for that?
Okay, just repeat your question.
No, we can change the definition of complexity profile, including conditional complexity, and then we, or even not doing this, independently of this. So we enumerate all elements which have smaller complexity profiles. And we know that if there are few of them, then they will be easy and the profile for Z will be not right. But you somehow claim that the number of elements which have close profile, not
Yeah.
bounded, but
Yeah.
even close profile is large. So how do you say why it's the case?
Okay, no, probably you want to say this. Okay.
No, I forgot this again. So
Okay, we take those Z prime in this extended extended set of clones that have a maximal or almost maximal complexity conditional xy. And then we observe that if this conditional complexity is close to the maximum, then actually every complexity in every coordinate must be close to the maximum.
so we have fixed x and y. So yeah.
But I'm afraid it should be obvious to those who has to those who have seen this argument before, not clear for the others.
Yeah. It's confusing, definitely. But let people ask. Let people say whether they want to hear this argument or to see how it's used and skip it temporarily.
Okay, yeah, I propose to skip the proof of this fact. Just believe that it is true. We will use it, and then when the proof based on this fact is finished, we can get back to it, and if people want to, we can prove it.
So this constant is universal somehow.
This constant, of course, it doesn't depend on x, y, and z. It's okay. It depends on the number 3. If we want to repeat the same trick for a tuple of strings of length 5, the constant will be different. But of course, it doesn't depend on specific x, y, and z.
I see.
Okay, so what is it all about? We're trying to implement the idea suggested by Sasha. Sasha suggested to fix x and y and variate z, and take the set of all z such that this diagram, this picture with complexities, looks the same or almost the same. And what we were discussing on the next page is the claim that if we understood this almost the same in a reasonable way, with algorithmic precision, then the number of different z prime here will be close to the maximum that we can imagine. And maximum that we can imagine in this picture is 2 to the n3. Just because the conditional complexity of z prime given the fixed x and y is n3. Okay, so we take the set of all clones of z, and yeah, it's all the same. It's all the same. This is what we have seen before, and now the lemma, which claims that the statement where Sasha was not very sure when he told that of course it is not true, but then he changed his opinion to okay, who knows, maybe this is true. This lemma claims that Sasha's conjecture is true indeed. The set of clones, the set of all clones, is a cluster, and it is a cluster with standard parameters. Okay, let us go back to the
So
picture.
the size, we already know the size. So
Yeah,
the question is whether we are the distance is bounded
log
by
size
the same.
log size of this cluster is n3. more or less, with logarithmic precision. We already know that. And it is easy to guess what is the desired diameter of this cluster. So the best we can hope for is that this central part, the size of n0, is common for all z prime from the cluster. So all those clones must share the same n0 bits somehow. And what we variate are only the remaining n3 bits. So complexity of each z prime is approximately n0 plus n3, and conditional complexity of z prime given another clone must be approximately n3, because of this n naught or n0, this will be their common part, and the conditional complexity is n3. So log size is about n3, and the diameter is also around n3. This is what we want to be true. And Lemma claims that it is indeed true. So this thing, this is what was n3 on the picture. And all other stuff you can ignore it, or all these big O of delta or log something. These are the terms that are negligibly small for us. This is the key statement. So this lemma saying that the set of all clones is a cluster with expected parameters. When we are done with this lemma, the theorem follows very easy. So, any questions about the statement of lemma?
Yeah, so we somehow need to consider two elements of this set and somehow to get the bound for the distance.
Yeah, we take two clones of z. This must be z 2 prime. We take two different clones of z, and we must show that conditional complexity of one clone given another one is small. And to this end, we will write some inequality. Now I will write some magical inequality. Just the inequality itself is true for any x, y, z, z prime, z2 prime, whatever are their properties. So right now I'm not using anything about our strings. I don't use anything about the complexity profile, about the definition of these clones. Just a universal inequality that is true for any 5 strings. So this is a slightly extended version of the inequality by Zhang and Yang. Sorry, why it doesn't work? What happens?
What doesn't work?
My tablet. Now it works. Okay. Okay. In Zhang Yang paper, there was a version of this inequality with 4 strings. Okay, a similar inequality for Shannon entropy with 4 variables, and with 5 objects. It was proven in our paper with Kost and Yura-Makaruchev and with Vereshchagin.
But this inequality was proven before, or it was proven specifically for this task? I don't remember.
No, it was
before.
It was proven just before all the story with
With
clusters
triples.
and with triples. It was proven as an attempt to understand the ridiculous proof of Zhang and Yang. So here again, if I write here log n as this additive term, then this inequality is true for any x, y, z, z prime, z2 prime of length n. Just such a fun inequality. Why it is interesting, why it was clear that it is interesting even before all this story, because this inequality cannot be represented as a combination of standard Shannon type inequalities saying that the mutual information is non-negative, the conditional mutual information is non-negative. It is something significantly, something substantially stronger than the standard inequalities for Shannon's entropy or for Kolmogorov complexity. Okay, so let us take this inequality provided by our Chinese friends, and let us see what we get in this inequality for our specific x, y, z prime, z2 prime, etc. I will change the color. Okay. In fact, if we look at the right-hand side of this inequality, then most terms on the right are negligibly small. So let us start with this guy. The mutual information between x, y, and z. X and y given z, this part. This is what we say is bounded by epsilon. Where it is? Yeah. X, y, and z. Then observe that since z prime is a clone of z, then the mutual information of x and y given z prime must be the same. Okay, of course with this precision delta, with this logarithmic precision, but it is also small. It's bounded by this epsilon plus delta, and the same here. And there is one other term, the mutual information between. No, two other terms. The mutual information between x and z given y and z given x. X and z given y and y and z given x. I will change the color orange. These orange terms. Let us see these orange terms. Let us find them on the picture. This is one orange term, and this is another orange term. And they both are also bounded by epsilon. They are also unknown to be small. So these orange terms are small. So when we forget about small terms, what remains here? What is not known to be small? This term, the mutual information between x and y, which is not at all small, and the mutual information between z prime and z2 primes. So this is what we get. The mutual information between x and y is not greater than the mutual information between z prime and z2 primes, plus something that we can ignore. And I propose to read this inequality not from left to the right, but from the right to the left. The mutual information between two clones z prime and z2 primes is large, it is bigger than the mutual information between x and y. This is what we get from this quasi-Chinese inequality.
And what we
And,
are interested in is the distance between them.
Yeah, what we know is the distance between z prime, the two primes, that is the conditional complexity. And now I just do the standard computations. No magical tricks anymore. The conditional complexity is the difference between complexity of one clone and the mutual information between two clones. Then I use our magical inequality. It is not bigger than, it is not greater than the difference complexity of z and the mutual information x and y. So why I write z without primes? Because z with two primes is a clone. It has with a precision delta. It is the same complexity of the clone has the same complexity as the real z, and the mutual information between two clones is at least the same as the mutual information between x and y. And what remains, the difference between these two guys, again we can see, we'll see now, we'll see it on a picture in a minute. It is what was n3, exactly what I want. So I want to know the difference between complexity of z and the mutual information of x and y. Let us see it in the picture. The difference between the mutual information between x and y, this thing. Oh, sorry. It was wrong. I want to take the difference between complexity of z, of all this stuff, complexity of z, minus the mutual information between x and y, and minus the mutual information between x and y if we don't care about small terms. So what we deduce, we really deduce the yellow part. It is actually it is the central part, the n0 bits that are common to everyone. So once again, I subtract from the complexity of z, I subtract the yellow part, and what remains is this guy, which is n3. This is exactly what is written here, in the formula. So we have proven that the distance, the information distance between any two clones is at most n3 plus something that we can ignore. Okay, so the main lemma is proven, and the main lemma is proven, and now we can use our main theorem proven last time, 2 weeks ago, which claims that in a dense cluster there is the kernel, extractable kernel of the expected size. So let W be this kernel in a cluster. In our case, the size of this kernel, it is this n naught. The size of the guy in the middle. And by the definition of a cluster, something is
There is some noise. Yeah.
Okay.
Now it's better.
Okay. By the definition of the cluster, it must have a negligibly small conditional complexity given any element of the cluster. That is, given any clones. This is the first property written here. And the second property, it claims that the conditional complexity of element of a cluster given the kernel it is equal to the diameter, approximately equal to the diameter of the cluster. In our case, it is n3, which is complexity of z given xy.
So this sounds good, because if z is since we know that z is an element of this cluster, then v is some part of information is in z.
Yeah. So I will come back again to the picture. So the plan was to extract the mutual information from the triple n1, n2, n3. And we expected that the size of this mutual information here, it will be this n naught. We haven't done this yet, but we are pretty close. So instead of extracting the mutual information from x, y, and z, we have done a strange thing. We have created lots of clones of z. And we extracted the common information, or the materialized this mutual information from all these clones. So far, the only good news is that our z, our string z, it belongs to the set of clones, so it also contains this kernel w. But we need somehow to show that this w, which is the kernel of all clones of z, it also belongs to x, and it also belongs to y.
And also we need to show that it has large complexity, right?
Actually, it is already automatically true.
The kernel complexity is the size of the cluster, so we know it.
Why? Why is this?
First, the clustering lemma, it says that complexity of the kernel is not greater than what we expect.
And why is this?
No, just if we take a kernel or no, because the cluster consists of elements which have small complexity relative to the kernel. So
Okay,
the cluster is large. So we know the elements of the cluster. So we know that kernel should have high complexity.
Yeah, we know that complexity of the true z is any other element of the cluster, given the kernel is at most n3. And complexity of the kernel is at least n0. I don't write these negligible terms. And it means that both these inequalities must be tied. They must be actually equalities. If not, then complexity of z would be smaller than what we expect.
Say it again. Why we have upper bound for the complexity of the kernel?
Let us go back to the theorem. Yeah. Here is the statement about the cluster. Uh, no, just sorry. I'm saying something stupid. The theorem about the cluster, it says that. Sorry, no, it doesn't work. Okay. Sorry, just I'm lost, but we will find the explanation. So no, we don't have this. We have a complexity of the kernel given z is approximately 0. Yeah. That's enough. Okay, just I will draw a picture for z and w. Complexity of w given z must be 0. Complexity of z given w is at most n3. And complexity of the entire z is n3 plus n naught. It follows that this n naught, it must be here. Okay?
So we have large complexity of W.
So a W must be of a large of complexity and not, and also this inequality must be tight. Yeah, actually, we have just discussed what I was supposed to write here. Complexity of this kernel W. It is this and not. And what remains to explain is that this kernel is extractable from X. It is extractable from Y. Okay, let us explain why it is extractable from X. We look at all here is a set of clones.
Oh, you want to say that there are many intermediate things?
Yeah, there are many paths of length 2 from X to W, where here the condition complexity of from X to Z prime is the same as from X to Z, which is n3, and from Z prime from the clone to W, it is approximately 0, negligibly small. And the number of clones, it is approximately n2 to the n3. And from the lemma that we discussed last time, it follows that that many paths of size 2 can be contracted to one short path of length approximately 0. So we have approximately 2 to the n3 paths where the sum of conditional complexities is n3, and it follows that complexity of W given X is close to 0. And of course, the same argument works for Y. And this is the end of the proof. questions?
No, things somehow match very nicely, and it's again this is not clear what to do with the bounded complexity, bounded space complexity, but
okay, this is the theorem that we have proven that. So last time we have proven that in a dense cluster there is the kernel representing the mutual information of all elements of the cluster. Now we have proven, we used it to show that in a triple we can, in a triple with these three small terms, three conditional mutual informations, we can extract the mutual information of all three objects. I think we have 10 or 9 more minutes, and in these 9 minutes I can explain how to get another corollary from this corollary. So
yeah, okay.
we will use the theorem to get one more conclusion.
Before you start, as a quick announcement. So now our timing is more tough because we have another conference just next 2 hours. So we will finish at 8:10, 10 past 8.
10 past 8.
If we do not finish willingly, somebody will just shut
Oh,
up.
so you mean it's technical thing? It's not that you need to go somewhere. It's just a technical Zoom requirement.
Yes,
Then
technical.
we can use other Zoom account next time. Okay.
Okay.
But now it's okay. Yeah.
Okay. So here is the corollary I am going to prove that actually we will need most of the time we will spend to understand the statement, what's written here. So we have discussed already the property of extractability of the mutual information, or this the difference between the common information and the mutual information observed by Gach and Kerner. So let these are our x and y. Here is n naught, n1, n2. The question whether there exists a w such that complexity of w given x is negligibly small and complexity of w given y is negligibly small. For some pairs x and y it is true, such a w exists. For other pairs x and y with the same complexity profile, it can be false. This is the difference between this example 0, example 1, example 2 that we discussed. Now, let us consider the following situation. Imagine that besides x and y, there is another string z, which actually has nothing to do with x and y. Technically speaking, the mutual information between x, y on the one hand and z on the other hand, this mutual information is negligibly small. You can understand this negligibly small as you want. It can be logarithmic or just epsilon n, something that we can ignore. And imagine that this oracle z, this z that has nothing to do with x and y, can be used as an oracle which helps to extract the mutual information between x and y. That is, there exists w prime such that, here we want w to be equal to n0. So there exists w prime such that complexity of w prime given x, and this useless z is negligibly small. Complexity of w prime given y and z is approximately 0. And complexity of w prime given the same z is what we expect, it is n0. In other words, we can materialize or extract the mutual information between x and y, but strangely we use for this some oracle z, which apparently cannot help, apparently cannot be useful, because because the mutual information between x, y, and z is nothing. So how can it be that some useless z helps to extract this mutual information?
Andrei, does it imply, I mean, this inequality, this equality, does it imply that the common information between x and y conditional on z is the same?
Yeah, just
Okay.
since the mutual information between z and the pair is 0, then the same is true for complexity of x separately with this oracle and y separately with this oracle. So these numbers, these coordinates in the profile, they remain the same when we add the oracle z.
Uh-huh.
So the mutual information remains the same. And in addition, it turns out that we can extract this mutual information given this oracle. And the claim is quite natural. If it happens, then actually we can do the same without any oracle. The useless oracle z cannot help. Or, well, if it helps, then we can do the same thing without z. There exists maybe some different w of the right size, which represents the mutual information between x and y without any oracle z. So the statement is pretty natural. It's easy to believe that this must be true. But to prove this natural statement, we will need the technique of clusters. And to prove this statement, I will go to the next page and I will write a diagram for x, y, and the pair w prime and z. Here is the picture for x, y, w prime, and z. And the picture looks like this. We have n0 here, n1 here, n2 here, approximately 0, approximately 0, approximately 0, and I don't know what here. There is no argument, just we need to write accurately all complexity terms for this new triple x, y, and joined z, the oracle, and w prime, the mutual information extracted with the help of this oracle. We have a picture.
But you said before that w prime. What is the w prime is information we extract.
Yep.
And where is our oracle? It's missing in the picture.
No, it's added to w prime.
I mean, on this picture, there is no w, right?
No, w.
No, there is
W is not is what we want to no. W
we want
prime
to we want to show that w exists, and what we know What we know.
Wait.
Conditional to Z, we can
W
find
is
some
given to us.
No. What is given is W prime.
And where is our oracle? Our oracle is Z. Sorry,
Z.
Our
sorry, I
oracle is Z.
confused.
So with additional oracle, we can extract X and Y common information, and we denote it by W prime. And now we want to construct the common information without an oracle. And for that, we construct the triple.
And
then
we look at the
know
picture.
that we can just use this.
Yeah, and we see that we have zeros in these for these three guys, and we can apply the theorem about mutual information of a triple, and this will be the mutual information extraction of the mutual information between X and Y, and that's all.
And so you say that all this zeros are just the result of computation with the
Yep,
what
yep,
is
yep,
so
yep,
nothing really happens here.
Nothing really happens.
Yeah.
Yeah, and if you're satisfied and a bit amused, I can tell you where is the trouble here. There is no cheating. The corollary is proven. It's okay, but in this corollary is proven for the case when the size of W prime, the size of W prime, complexity of W prime, given the oracle, is n0. That is, we extracted the entire mutual information between X and Y. But assume that we have a weaker condition. Assume that given the oracle Z, we can extract maybe not the entire mutual information between X and Y, but I don't know, a half of it, or 25% of it. Just some part of the mutual information can be extracted given the oracle.
So you mean that there is a string of this complexity which is simple given X and Y?
Yeah, there is a W of size not n0 but n0 prime, which is smaller than n0.
Say half of zero and
Yeah,
zero.
yeah. 1/2 of n0. Then it is natural to expect that we can get the same thing for W without prime, also of a smaller size, with the same precisions. But as you can observe, the argument doesn't work anymore because we don't have a zero here anymore. But nevertheless, I have no time to explain you the argument. Nevertheless, we almost can prove it. Almost in the sense that, okay, when we prove the statement about the extraction of the entire mutual information, the precision here on the left, where they were just a little bit worse than the precision on the right. So if the precisions on the right are logarithmic, then the precision on the left are also logarithmic. Maybe the constant in this O log n term is a little bit worse. But if I want to prove the same for the half of the mutual information, then the only argument that I know gives a much weaker precision. So we start with the precision log n here and get a precision something, I think, square root of n over log n, something like that. We get some ridiculous precision here.
But this is without the assumption of stochasticity.
Without assumption of stochasticity.
And with this assumption, you get good precision.
Yeah. For stochastic pairs, we can prove it with the right precision. And for a general X and Y, we have a strange proof with a strange precision.
But this
It's
proof
probably
use
an artifact
clusters or it uses some other techniques which is different?
It uses an adjusted technique of a cluster plus some other dirty tricks. So perhaps the statement is still true with the right precision, just we don't know how to prove it.
Yeah. Okay. Okay.
And okay, this was written in our paper with Muchnik. Okay,
But it is not
perhaps
in your new survey paper.
no.
And the previous one is written.
Yeah. So this is probably not the last paper of Muchnik, but this is certainly my last joint paper with Muchnik.
Okay. No, I don't know whether it's all very strange for me, this cluster technique. Maybe what we could look at some point we can look at this even more strange proof. And Corey, what do you think? Should we, or it's too much for now? Not for now, but just.
We can wait.
Okay, so for the next time, there were two plans. First, there is a talk of Ushakov, who should speak from the. He implemented some kind of text processing using these new tools, and I asked him to explain details how it works and how it happens, and so on. And also, we have being at CIRM, we met Ivan Titov from Heidelberg, who can explain the rather new result of Barn-Palias about random Laurent semi-computable number. There is a very strange thing. There is kind of very precisely defined speed of convergence. So there are the most slowly converging random series with computable series of rational numbers, and they all have exactly the same convergence speed, just in terms that this ratio of tails tends to some constant. So we can ask him to do it next time, and ask Ushakov to be 28th of March.
Okay, next time is Ivan.
Ivan, I will send the and maybe
Okay.
we will ask, I don't know, him or maybe Laran or myself. We'll try to get some initial explanation about the context, what is happening or not happening there.
Okay.
Yeah, how it's possible that we have two copies of Andrei?
There's this technique of clones.
Yeah. But you are somehow from different angles.
But
So we have
it's okay. The clones are not identical, but indistinguishable.
indistinguishable.
But the distance is very small between them.
Distance is very small. Yeah. No, I see you are in the office and there is different angles.
Да, ну все, нас сейчас выгонят,
Да,
так
да,
что,
давайте
окей.
самое. Пока надо выключить запись, пока она не потерялась.
Нет, запись не потеряет.
Даже если выгонят?
Да, даже если выгонят.
Не знаю. Ладно.
Вот, ладно, я сам тогда закрою.
Ладно.